Hi, I'm Rashad.
Hi, I'm Jonathan. I'm Tyler. I'm Jason. I'm Dennis.
And this is playground physics.
I was here to help.
Yeah, that's alright.
To the balance of the two group members have on the torques exerted on the teeter totter. Anyone got it?
Wait, I'm still confused.
Well, for the smaller person, we had to increase the distance from the fulcrum to increase torque.
Right.
And for the bigger person, he didn't have to go as much from the center. So we
moved him closer.
Yeah.
So
he was-
we
so-
decreased
so
the
they
torque
equal the torques.
of the heavier person and increased the torque of the smaller
Yeah.
person.
Why does that change though?
Well, what do you mean? Why
Does that affect
the balance?
Yeah.
Because the torques should be the same. So the smaller
Yeah.
person has to sit farther away so that his distance is greater.
If you're further away from it, you will affect the center more. I don't know. That's what happened.
Your torque will be greater.
Yeah, you have a greater effect
are
on the
from
center than if you're closer.
Yeah,
because
yeah.
your effect won't be as
So
felt.
the next question is, what can you say about the sum of torques exerted by the two group members on the teeter
They
totter?
should be at equilibrium
No.
for the thing to be balanced.
The two torques should
The
be
two
the same.
torques
They should
but,
be the same.
But what would be the sum? Would the sum be double them or would it be zero?
Zero, because it's at rest.
Yeah.
It should be at zero because
Yeah, it's not moving.
it's
No,
equilibrium.
but
There's no
the
movement. There's no movement.
Yeah.
But they're both going down, are they not?
Yes, but it's across a fulcrum, so when one goes down, the other one goes up. So actually, technically, the force on either person is actually going up from the other
Yeah,
person.
so it should equal zero. How? Because they're both positive.
No, because Jonathan, think about it. If I'm talking about me on one side.
Yeah.
So in the end,
They
they're
counteract
both
each
up
other.
and down.
forces.
You're right. You're right.
Yeah,
So it should
yeah.
equal zero.
The forces.
From the perspective of the spinning merry-go-round, what are the forces on the ball as the merry-go-round turns? From the perspective of the observer on the ground, what are the forces on the ball? After the ball is dropped, which observer's forces are useful in describing the ball's motion?
Okay, so
There's
as
FG.
as the observer,
As the observer
The-
and the
as the
From the
observer,
merry-go-round, there's only gravity.
yeah, that's what I was saying.
yes,
Only
but
gravity.
from the observer there's gravity and then the merry-go-round force, which is the applied force, right? So we have for me, which is the observer, we have FG and then FA.
Wait, but FG should be. In reality, FG should be the only one acting on it, right? Or does
Well, no, because the
no? Your applied force also matters.
yeah,
because
exactly,
you're
yeah,
pushing
yeah,
outwards. Yeah. So,
And so
the
from
only ones that are applied force.
But from the
oh,
per-
and FN, right? Because my hand is technically FN holding it up.
No, it doesn't matter.
Yeah.
It
because
doesn't matter. 'Cause they're not
FN doesn't
touching.
matter, but
they're not
it-
touching though. Like they're not touching for the majority, like for the ball.
my
it's not
hand,
touching. No.
it's holding it. That's the
But
only
that
reason
doesn't
it's not
matter.
Doesn't
out.
matter.
Are we talking about the moment we dropped it or the moment
No,
before we
when
dropped
it's going
it?
through the air.
While it's spinning.
Okay, yeah.
It'll just be FG.
And so
FG
what
no,
was
FG
wait, there's three
the
things.
speed of
You
the
said the
speed.
perspective.
After the ball is dropped, which observer's forces are useful in describing the ball's motion?
We also have a horizontal motion though.
Yeah, that's the
Yeah, that's what I said. FA.
Yeah.
Kind of, yeah.
Yeah,
from the
FA.
merry-go-round.
From the merry-go-round.
So the only ones
Yeah,
that
so
are
whatever.
affected are FG and FA. That's
So-
it.
And so
Which one?
the person who's right is on the ground, right?
No, but Yeah.
Wait, hold on. If I dropped when I dropped right in front of you, was the ball like in front of you or like to the side?
No, when you drop it here, it goes like this.
Exactly. So then it should be the guy on the
Right. So
merry-go-round.
it should.
Because he has to FA after
Yeah.
the ball.
So FA does act on you because it drops further from. It drops
That's what I
away
said.
from-
That's what I said. Yeah.
Yeah, so from observer, it's like a line. It follows a
Yeah.
slope, right?
Yeah.
And then from the person, it's always in the same line,
Yeah.
but just going straight down.
Yeah.
Yeah.
So the person who's no.
So for me, it was just FG.
The most useful one is
Merry-go-round
the
just sees
person.
FG.
Right.
Yeah, because their FA is the same as the ball's FA, so they're actually
Right. Yeah. So there's no
the ball's like at rest
Same thing
horizontal.
about when we were quoting Tyler, because you were also spinning on it. There was no change in like this.
I was too busy.
It was just
Yeah.
basically- yeah. Okay.
But now we have merry-go-round. So
Okay. So
what would happen if your feet slipped while you were spinning around? Would you fly off away from the center of the merry-go-round?
I
Would
think
you
we know how to
would you
answer that
continue in a
question.
straight line? Would you fall towards the center?
Let's ask Jonathan.
yeah, Jonathan, did you?
Well, remember, this is the one where you're walking towards the middle. He was just standing. So if you're walking towards the middle and your feet slip, you should go away from the center. Actually depends on which way your feet slip. Because
Yeah.
your feet slip back, you go forward.
Yeah.
If your feet slip forward, you go back.
Yeah.
I think no matter what, you slip back.
Really?
Because when you take talk about slip, right? She means like no force. If you slip forward, then you're actually putting a force forward.
Yeah.
Not
But
force
aren't
forward.
you moving forward? So wouldn't you be putting force forward anyway?
No, when you slip, you fall straight down.
And you're saying, why would we be going backwards and not like side to side?
Huh?
Because when you
Because
slip,
that's the movement.
when you slip, don't you have momentum going like turning? Or is that
No, okay. Think about like, if you're already spinning and there's like a piece of the merry-go-round missing, you just fall straight through it. You don't fall this way and like, right?
Yeah, the friction.
But don't
the
you have
friction from the
acceleration
merry-go-round
that's
does keep you
constantly
there.
changing? So
So you'd fall away from the center, right?
Yes.
No. Wouldn't you be falling?
We can go test that, Jonathan.
No, you're only going to be falling away from center. Because think about when you spin, right? There's a centrifugal force that pushes you outwards, right? But then you're holding on. That's why you're still there, right? Or you're friction between your feet.
Yeah.
But then-
yeah.
But then think about when you let go, right? The centrifugal force is going to throw you, right?
Yeah.
But then you go in a straight line then. But you're saying like, the force is just like it's constantly curving,
So
right?
you're going straight line and outward.
You'd form like an L, right? But the only force that's holding you in is you.
Yeah.
So if you remove that because you slipped,
Wait,
right?
haven't we tested this in physics?
You're gonna go in a
class
straight line.
before? Have we tested this? In
Yes,
remember,
we did.
Yeah, with
you
the marble.
circle and then
Yeah,
the ball goes
yeah,
like
yeah,
this.
yeah, yeah.
The ball.
Marbles in the
The
plates.
ball goes like this, right?
Yeah, the thing goes in a straight line out from that point.
Yeah. Okay, so it'd be
So
straight
you go
line
away from
and
center.
away.
It's out, of course.
Yeah.
It has to be like a line tangent to the circle.
Oh yeah.
Well, no,
Michael Derivative.
no, it wasn't.
Yes.
It was, because
Wait.
like,
Well,
technically-
yeah, since you're from the inside, right? But you'd follow the same path.
Yeah.
The only problem is you'd be inside the circle, so
Hey, by
we
the
have
way-
a bar here, you'll hit a bar or something, bounce back.
There you go. This isn't special.
Superman!
What happened to the period of revolution when the person walked towards the center?
I feel like it slowed down.
The period of revolution, like the amount of time it takes for them to go around in like circles.
yeah,
increase.
it increased.
Wait, the closer you get.
I think it
the
should.
closer
I think it should decrease. I think the
No,
problem
wait.
is
No, because the thing's slowing down.
no. The thing should decrease. The only problem is we have other factors like friction and the fact
because
that we is not pushing
when
anymore.
When you let go, it's the fastest, and then it slows down. So once you
Yeah.
guys got into the middle, it had slowed
It
down.
slowed down, but it should. But if
It should get faster if the mass is close to the
If it
middle.
kept its speed, it would have decreased. If it kept its speed, the time
Like
would have decreased.
the period of our outers are always less. Yeah, the one period of just one.
Wait, shouldn't it be
revolution
greater?
always- No, they're always less because it slows down. The merry-go-round slows down, so one revolution is much slower, and you guys just walk slow.
Yeah, that too. I do walk very slow.
You guys just walk slow.
But it should go. It should
Yeah,
get
if-
But yeah, the
If it
period of
kept-
revolution
if
is
it-
definitely
if it-
shorter.
if it
It's just
kept
that
the
it's just
velocity,
that
yeah.
he's walking slower, so it should
Yeah,
walk.
yeah.
Did the speed decrease, stay the same, or increase? How do you know this? It decreased because it's slowing
We
down.
just stopped pushing it and
Yeah.
Yeah.
stopped it.
Exactly. It's not. What's it called?
No, but okay.
Friction is not
If you had kept continuously pushed it and you walked in the middle, what difference would that have made? I think that would have
Difference to what?
like
would've been
if it didn't slow down because of friction.
It
and
actually
kept
would've-
spinning,
it
but
act-
you moved to the center while it was doing that.
It actually might have taken him longer because it's harder to walk when it's going faster.
If he
That's
was
only
in
because
the
he's
center-
busy.
Like in a frictionless world. In a frictionless world.
Assuming it would be slow.
Yeah.
Or
Yeah.
faster.
Faster.
I walk, I mean,
Yeah.
It's like an ice skater.
Yeah. Oh, it's like if you go like this. you
Yeah,
go-
it's like an ice skater.
Orbits, right? Like,
Yeah.
Mercury's
We're
orbit's
talking
faster,
about
right?
revolution,
So
Jonathan.
less.
Yeah. So you okay in a frictionless world? If you walk in the middle, it should increase. in
Yeah,
speed.
because
Yes.
remember, like, this will be like the planets. Mercury's orbit is faster than everyone's
Yeah, right,
orbit
right,
because it's
right,
small.
yeah.
Yeah. What must happen to the person's speed then if the angular momentum is to be conserved? Did you observe this?
Okay.
Okay, can you repeat the question?
What must happen to the person's speed then if angular momentum is to be conserved? Did you observe this?
So it would be the same if it's conservative.
Yeah,
I'm
what's-
assuming?
What is the formula for angular momentum?
Probably like.
It's on the back page.
Yeah,
Yeah.
it's on there.
L equals what the heck are those?
Read it.
Is it a theta?
It's not theta.
No, it's not.
Is it a mu? What is it?
No, what the heck
What is
This
that?
is over here.
Why are you looking at me? I can't even see the formula.
Is that I times what?
Tyler,
What's
Tyler,
that?
there's a
I
problem.
is moment
Tyler,
of
I'm almost
inertia.
approaching
What's this?
60 gigs now.
Angular velocity.
60.
Angular velocity.
I'm on
times
42.
moment of
Tyler,
inertia.
I'm like 40 gigs
Some-
right now.
And a moment of
Angle.
inertia is equal to m times r times r.
What's R?
I assume it's for rotation.
Rotation speed, revolution speed.
Capital R, lowercase r?
For dumbbell.
What's how you?
No, R is lever arm. R is lever arm. Distance from center of rotation. So distance from center of rotation squared times m, which is mass.
What's the mass of the thing?
So the
The
person, right?
person. The person. And then you multiply that by angular velocity, which is equal to
Rotation through some angle.
sum of what the heck? What is that?
Rotation through some angle divided by the time left. So the angle is
Wait.
360. which is
Sum of time over what is that? Sum of what? What's the sum?
over the sum of time. Sum of angle. How much
Oh, that's
angle?
theta?
Oh, okay.
That's theta.
Oh, my
So
fault.
it's 360 over how much time is elapsed.
But your rotation is. Right, you're going
Right, that's why we're
multiple
timing
rotations. But
it.
you're going multiple rotations. So.
Both times how
No,
much
we're
time
talking
is
about
elapsed?
one. Yeah,
okay.
one.
It might be
So
too
go
far
back
to
to
be
question.
heard.
What must happen to the person's speed then if angular momentum is to be conserved?
So if the angular momentum is to be conserved,
The
that
person has to go faster.
Why-
Slower.
No.
Because the revolution is going to be faster, no?
It's being conserved though. It's no. I'm pretty sure there's.
it's m times r squared times the change in angle, which is always constant over the time. So if the person's speed is conserved,
So the change in angle will not change.
Yeah.
The time
Yeah.
will.
I'm-
the mass does not change.
that's
No,
not
the time.
change.
Wait, the time will not change either. Per
R
rotation.
doesn't change
It does.
either,
Being
right?
conserved.
Does R change
Being
either?
conserved. What's
Okay,
the-
so R changes and time should change.
Wait,
So
what's
why?
how would be?
Wait, why?
Well, because if you move closer, the rotation speed is less. Like the time. for
Wait.
is less.
So we're talking about what's different to angular what's the question again?
What must happen to a person's speed if angular momentum is to be conserved
During this whole experiment?
during the walking in?
Isn't the length shorter then?
Yeah.
So we're shortening the length.
So
But angular momentum must be
the person
conserved and
has to
speed
go
must be
slower.
conserved. So something else has to
So the person has to go slower.
something else has to increase.
It would go faster.
No.
No, you have to go
The
faster.
length is
The closer you
decreasing.
get, the faster you
The length is decreasing, but the length multiplies
Oh,
in.
so you're saying the person has to go faster.
Yeah, the
Of
closer you
course.
get to the middle,
Wait,
the
why?
faster
Wait,
you
wait.
go.
I'm confused.
Think about the equation, right? If it's conserved, it has to equal the same, right? So if the length is shortening, it's getting smaller. Something else has to increase, and it's not the speed because it's conserved, right? So then something else has to increase. And then if you go inside,
Total is increased.
Yeah. Okay. No. Okay.
it says it's conserved.
Conserved.
Yeah, it's
When, okay, but Mike,
Yeah, so
but
it's
Michael,
equal.
think about this. If you're walking at the same speed, but the length is decreasing, wouldn't you be walking? Wouldn't the time be decreasing as you
Yeah,
walk slower?
it'd be faster.
So wouldn't,
The
it
thing-
be that, wouldn't that mean you'd have to walk slower?
Yeah, that's what I was
No,
thinking.
it's it spins faster.
it's
It's been
Wait,
same.
what?
It has to spin faster.
No,
Why?
we're talking about the person's speed.
Yeah.
They still go faster now.
No, they go slower.
If the thing spins, they
It's
spin.
the spinning speed because you're stuck on.
No, he's talking.
See, he has to be going faster though.
That's the lever arm, right?
No, I agree with yourself. If the length is decreasing, you have to go slower to match the same speed as
Yeah.
previous. If your length is
Yeah.
increased,
There's no match
No.
at the same time. Match at the same time.
Yeah.
No, but if you match the same time and your length is shorter, your angular momentum is not conserved
Well,
No.
It's not.
because the length is
The lever
shorter.
arm is decreasing.
It's multiplied in, right? So slower. So for example, like if you how much force do I have, right?
Wait,
if I
so
go
you're
to
saying
slow,
if by increasing the speed of this
Mhm.
merry-go-round, my
Right.
personal
Right.
speed is
Moment of inertia,
increasing.
which is,
Right, my personal speed is decreasing.
because you're not going as far. Your arm length is shorter. Your momentum is less
Either
then.
way, right?
Either way.
Shorter length, less momentum. So then you have to increase speed to balance it out.
They're all directly related. Yeah, so if one's decreasing,
They're all directly proportional.
And the other must increase.
They're all directly
1
proportional.
half times 2 versus 1 times 1. Yeah, but same thing.
how would distance and speed not be inversely proportional to keep the same time? How does it make any
You're
sense?
not keeping the same time.
Yes, we are. That's
rotate
what you
faster.
want.
You're not
You
rotating
want-
faster.
No, you want to keep the same time, don't you? Because that would make the angular momentum the same. If you
Angular
keep this,
momentum
if
is
you,
concerned.
No, you want to keep
if this
everything the
ratio is
same.
It's the same.
You want to make them all multiply equal to the same.
No, but R is
So-
changing because you're walking towards the center.
Yes.
So if R is getting smaller,
Yeah.
then one of these things has to get bigger.
Wait, how's R getting smaller? I'm confused. Wait,
Yes. Yes.
Because you're getting closer, Jason. You're getting closer.
You walk slower.
You're getting closer. The arm length's gonna change then, right?
But this has to increase.
As
so
the person
for
is
this to increase, you make
moving
time
to the
get
center,
bigger,
the people
and so you
spinning
walk
should
slower.
stop spinning, right? Should spin less. Because
But then you're
Right?
into
Of what varied had the greatest effect on the period of swing. So the characteristics we have were
Angle, chain length.
weight.
Oh, wait.
Yeah,
Well, I don't think weight affected at all. I
weight,
think weight
weight,
was the same.
chain length,
I
and
think-
starting position. Or
Starting
distance
position.
from
I would say starting
equilibrium.
position.
Just-
Distance
well,
from
you can
equilibrium.
just look at it.
Let's see what we can change our thing to this.
There's greater standard deviation for
It was arm length. Chain
Chain
length.
length, really?
Chain length, yeah.
But some of that could be accounted to just human error from your timing. Like
No, but like they were consistently going up. For the weight, they were roughly the same. Like
I don't think
I
weight
took
makes a
longer.
difference.
I took longer than Michael, but Michael weighs more than me.
Yeah.
And then Ari
Ari,
took shorter
took
than me.
more.
Yeah. That the weight did nothing.
Yeah.
The what's it called?
the starting
Yes,
position do nothing.
Starting
I think
position.
starting position has more effect than chain length.
But starting position wasn't consistent at all. It was like really weird. Like 31 was shorter than 10, and then
Oh, wait, maybe-
42 was longer than both of them.
Maybe since you're gonna get the momentum going. Because
Yeah,
I mean,
that's
like
what I was thinking
10,
too.
10
Yeah,
makes
yeah.
sense,
So
but
this
like,
bounce
why
there.
was 42 the longest? That didn't make sense to me. Like, I would have thought 42 would be the
I don't-
shortest
I
because
don't
I
know.
went faster.
But you're moving further.
You're right, yeah. So that I assume they would have equaled out. But
Yeah,
it
Yeah, I
didn't.
you're
think-
moving faster, but you're also moving farther. So that's why.
I mean, there's always sources of error though.
Yeah, but the most
That's what I'm
consistent.
thinking. It's like the
No.
difference is about like this. I feel like it's just your timing.
yeah,
That's if I'm being honest.
Well, no, I think the difference was I don't know, the way I
You maybe
when you
kick.
kicked off.
I don't yeah the way I lifted off.
Oh wait, and on one of them, didn't you like kind of kick off the ground?
Because there's a lot more. No, that was
Like if it
Ten.
was too short, like you said, like crap.
that wouldn't have changed it. Because I would roughly.
Wait, but aren't you exerting force? off
No,
the-
but that was at the end. I was coming back and
Okay,
my
yeah.
feet hit the ground.
Yeah.
So,
Okay.
Anything else for that one?
I don't think so. Yeah, nice one, Jace. You know the
Do it again.
Why is there rock there?
Jonathan!
From where you're sitting, right?
Wait,
We just measured the
did
same
you guys
distance
measure
from
40 inches?
No, I didn't. I measured 40 inches. You moved your pole to me. You moved your pole to me.
I measured 40 inches. What are we talking about?
This isn't the recording. That should have been a blooper.
We just have to go 40 inches back and turn higher. That's all we needed.
Yeah, no. If I'm moving 40 inches back, it should be the same height as the shot.
Yeah, we don't know where 40 inches is.
You
We're
get
measuring-
40 inches from right here. You pull it across the.
We're
right
measuring 40 inches. When do you guys get a tape measure and measure 40 inches? I'm not talking to this guy
Where's the tape
anymore.
measure?
Give me 40 inches.
Tape measure.
When do you guys learn how to use a tape measure and pull out 40 inches?
I can give you 40 inches.
Oh my god. I'm here all day trying to do 40 times.
Okay,
Come on.
I'm not trying to measure 40
He's
times.
right here.